So I will do number 1. Given a 90% confidence interval of 45 and 105 for mean heart rate, which of the following is the best interpretation of this confidence interval? And I put A. We are 90% confident the true mean heart rate is between 45 and 105.
That's what I put too.
Yep.
Good.
Okay, and then number 2, let's see, the researchers at the University of Mississippi wanted to determine whether the research time in seconds to go or no-go stimulus of males differed from that of females. The researchers randomly selected 20 females and 15 males to participate. The go/no-go stimulus required the students to respond to a particular stimulus and not to respond to other stimuli. Use this information to answer questions 2 and 3. The researchers decided to construct a confidence interval to determine if the difference of the means is significant. To determine whether the confidence interval would be reliable, they created QQ plots of both random samples and see that they are approximately normal. Are the requirements for constructing a confidence interval satisfied? Why or why not? And I put B, yes, the distribution of the mean of each sample is normal since the data have been determined to be normal.
That's what I put.
Awesome.
Then for 3, of the 4 types of confidence intervals listed below, which one is appropriate for this experiment? I put D, using independent samples.
Yep,
Did I get that
that's what
right?
I put.
Good. Okay. Number 4. A researcher is interested in estimating and saving account balance of customers at a large bank. She obtains the saving account balance of a random sample of 30 customers. A 95% confidence interval for the mean savings bank balance of bank customers is found to be $3,402.08 or $4,142.75. Which of the following would produce a confidence interval with a smaller margin of error than the 95% confidence interval? And I put B, obtain the balances of 90 bank customers rather than 30.
That's what I put.
That's what I put too.
Good.
Okay, so 5, a factory makes propeller drive shafts for ships. A quality assurance engineer at the factory needs to estimate the true mean length of the shafts. She randomly selects 4 drive shafts made at the factory, measures their length, and finds their sample mean to be 1,000 millimeters. The lengths are known to follow a normal distribution whose standard deviation is 2 millimeters. Calculate the 95% confidence interval for the true mean length of the shafts. And I put A.
I put B.
I put B.
You put B? Okay,
Yeah.
why did you guys put B?
Okay, so I did the formula that, so 1,000 millimeters, the sample mean minus the confidence interval, or not the confidence interval, I'm sorry, the, now what do you call it? Yeah, the 95%, the 1.960
Yes.
times 2, the standard deviation, divided by 4, the square root of 4, which is the number. So, and so that's how I did the formula. What, is that the formula you used?
That's the same thing I did. So when I put in the 2, when I do the 2 divided by the square root of 4, I get 1.
Right.
So when I times that times 1.96, it just comes to 1.96. So when you add that to 1,000, I got the 1,000 and 1.96, and when you subtract it, I got the 99.8.040.
Okay, let me see. What did I do different? Because I got... Let me look at it real quick.
Okay.
Square root of 4 is 2. So 1.60 times 2. I think what I did, and maybe what Karina did, is I multiplied the 1.960 times 2 to get 3.92, and then divided that by the square root.
You know what? I'm checking some of the past things that I've done. Like I used past examples from lesson 10. So for the preparation assignment and for the homework assignment, this is what I struggled with the most. I kept getting these answers wrong until I finally wrote down that I needed to work out the information. So I needed to do the deviation times the sample mean squared, and then times that by the number, which would be 1.96. So when I look at my past answers of things that we've done in the past, that's what I did to come up with the correct answer.
Okay, let me look. Yeah, so I think that's what I did. Is that what you did, Karina? You multiplied the top two first before you divided?
So I just put it into Excel and it brought up that answer. Because that's how I roll.
You're so much smarter than we are. You're in technology.
That's the answer that it came up with?
Mm-hmm.
Let's see. I'm trying to find, let me find my notes on that. Let's see. So I have...
So if you go to your notes, if you have your notes for the preparation assignment for 10, and you go to 8.
8 and 9, we did that, right? Okay.
Yeah.
Let me see how I did those. 1.960 minus 32 equals.
Let's see. Thank you, sweetheart. I'll have some later, okay?
Let me see what I did.
Yeah, I did the same thing on my 8 and 9 on that preparation assignment.
Let me just double check here.
So I'm...
What number did you get on that?
So for number 8, I got 532.18 and 549.87.
That's what I got too, but for some reason...
And then on 9, it's the same thing, and I got 534.73 and 547.27.
Yeah.
that what you got too?
534. Well, I got 534.72 and 547.27.
Okay, I probably just rounded that one up to
Yeah.
73 or something.
Yeah.
Let me just go through that problem again just to make sure.
Yeah, that's the only thing that makes me nervous.
Yeah. Right, because one answer is right and one's not.
Yeah. I'm like,
10.
oh.
Yeah, that's frustrating. Okay, 1.96 times 32 equals. The funny thing is I get the same thing either way.
So then we should come up with the same answer.
I would think. Let me just do, so that was on 9. Let me just do 8 again and see. But I think the numbers are
Well,
the
let me
same.
run through this problem and see if I get anything different if I do just write out the numbers.
Oh, wait. I'm trying to see. Like below, I have, it's hard to read my workout problems,
Yeah.
but I have the other done below it. I'm gonna pull up chapter 10 and look at that real quick and see,
Okay.
so we know for sure.
Okay, I'm gonna try the other way. I just did it the way you told me also, and I'm getting the same answer that I just came up with. The 1001.96 and then 998.04.
Really? Let me see. That's funny. Okay, let me do it again. So
2
divided by 2, obviously, is 1 times 1.960. So I'm doing it your way, 1.96. So you have 1,000 minus or plus 1.96, right?
Yeah, basically.
Yeah, 998.04.
Then I did it just the same way you did it, and I came up with the same answer. So I did 2 times 1.96 gives me 3.92 divided by 4 did the square root, and that gave me 1.96 plus or minus 1,000, which gives me the same answer.
Well, looking through my notes, I mean, that's what it's got to be then, is the 998.40.
Yeah.
What are you thinking, Karina?
I just feel safe with that one because that's what I got. I'm sorry. Say it again. Let me make sure.
On 5. So if you compute,
So when I put it in Excel, the
that by 2,
that it brought up
1,
that one.
and then times that by 1.960.
What number did you get again, Karina?
I got B.
Okay. So yeah, there's something that comes up differently on that.
Do you guys want to try putting it in SPSS and seeing if it comes up with one of the numbers that's there?
I don't even know how to put it in there. Do you know how to figure that, Ruth?
Not without more information.
So if you go to the first one, the sample mean is 1,000. We have a standard deviation of 2 millimeters. And
hold on one second. Let me go to Excel.
Okay.
And then see. Okay, so the mean is 1,000. Okay, why did it just go? Okay. Now, are you doing it on the one sample t-test?
Yeah.
I'm wondering if that's what the difference is. For confidence level. And then, is there a null hypothesis? Oh, no.
Cool.
Does it give us a null?
So the null doesn't affect the
information given?
Yeah.
So I can't really see in chapter 10 where it specifies, like, do you multiply first and then divide, or do you divide then multiply? But if you look at 4.2, factors affecting the confidence interval, the width of the confidence interval, 6, it talks about, since the sample size is the denominator, if n is increased, anyway, but it lines up the fractions first, and then if you change the confidence level, so you still have the fractions, but then the confidence level could be interchangeable. So it seems like we would do the fractions first, and then do the multiplication.
Doing the multiplication.
From that answer. You know, just looking at what it lines up on 4.2. I'm trying to see if there's anything else that specifies. I don't really know my mathematical rules that well. Like, do I divide first? Do I multiply first? And if none of them is in parentheses, that doesn't help me. So, because I know that rule.
You know, it's interesting too, because I mean, I'm looking at the Excel, and the Excel gives us that number, but when we do it by hand, it's not the right number. But that's when we were doing this information for this chapter, we weren't doing it with Excel or with SPSS.
Yeah, it was all by hand.
So that's kind of what makes me lean towards keeping it as A, but I guess.
And I don't really have anything in my notes that says divide first and then multiply, or you know what I mean?
Well, I didn't have it in my notes. And for some reason, something wasn't computing right one day, and so, you know, I was talking with my husband, and he said, "Well, you're not doing it the right way." So I started doing it another way, and then when I got on with the tutor, she confirmed that I was doing it the wrong way. So I'm like, okay, well, I'm doing it the wrong way. I'll just start doing it this way. So I wrote notes all over telling me that I needed to go back and make sure that I did the fraction before I moved on. Of course, maybe I'm getting my notes reversed, but I worked it out the way you had walked me or had talked about Kimmery, and that it still comes up with the same answer.
Yeah. And if I'm walking through some of the other problems in chapter 10, I've done the division and then multiplied.
So you were doing it the same way I was doing it?
Mm-hmm. In my homework assignment and the preparation work.
So I'm wondering, is this like, I mean, I don't know. This is such an interesting thing. I wish we could look at it again on SPSS. Trying to see if there's.
I don't even know what to put in there. Like, if that doesn't give me the information, I don't know how to import it into SPSF. Like, I wouldn't know what to put.
Yeah, it doesn't.
And where to put it. Because it's a little different than Excel. How it uses the data. Maybe I'll Google it. If I can find anything. If I can word it correctly.
Maybe this will be something. You know what I'm going to do? I am going to take information from our preparation assignment and put it into Excel.
And see what it comes up with?
Yeah.
That's a good idea. Okay. Okay, now this says...
It's interesting. I put the numbers in, and they are different when I put it into Excel.
Well, here's on Fastest website. Order of operations. Do things in parentheses first, which we knew, but that doesn't involve this situation. Next, exponents. Powers roots before multiplying, dividing, adding, subtracting. Then, of course, multiply and divide. So you do the power and roots first.
Okay.
I think that if I'm looking at this correctly, parentheses, so it has canvas, parentheses first, exponents next, multiplication and division, left to right, then addition and subtraction.
I did question 9 for 10 in the prep assignment, and when I put it into Excel, it gives me the base numbers are right, so at like 554 and 547, but the decimals are off. So when you work it out by hand, it gives you 0.728, 534.728, whereas on Excel it's 534.651, and then you get a 54 or 547.27, and then on Excel you get a 547.349. So there's enough of a difference in the decimals that I think I'm going to go ahead and keep the answers worked out by hand. Just because the answers on the answer key are the ones worked out by hand, at least for this assignment.
Yeah. I mean, that makes perfect sense, and that's looking back at, like, that's what I've done on most of them. But, you know, looking in chapter 10, I don't see anything that really specifies.
No, I think, well, being as I've worked it out the way that I was doing it and the way that you were doing it, and the answers came out the same. I don't know if you've received the same thing, or if you're still receiving the 9.
4 point, yeah, if you look at 4.14, the formula for confidence intervals, it looks like to me that x minus z multiplied by the square root divided by the standard deviation. So it looks like the x and the z are lower, like where the division sign is, opposed to being up where the standard deviation is.
Okay.
So if they were up, then it would look like you would multiply the standard deviation.
Hi, ladies.
It looks like you get that, and then you multiply.
Okay.
Can you hear me?
Yes.
Woo!
Hello.
Sorry I'm late.
No, you're good. You're good.
So what number are you on?
So we're on number 5.
Okay.
Okay. Do you want to
So
go
if
ahead?
we want to, so what did you get for number 5, Nat?
I put A.
Maybe we should just go with it.
What did everybody else get?
I got
No,
B.
She put B. I've got A, and then Kimmery had B, but I'm not sure if you're
But now I'm
working it
talking
out now and if
myself
you're
into
getting
A.
A. Yeah.
Then
See, I
think
confused
we just
myself.
go with it.
I get both answers.
Well, you know, that may be one where we just, you know, it's interesting because, I mean, using the Excel, it does give a definite different answer than what you do when you work it out by hand. It may be something where we just need to make a personal choice when we get to 5.
Yeah, that's true. What did you say you got on it, Manette?
A.
A.
Did you work it out by hand or put it into
I worked it out by hand. I have pages and pages of scratch paper.
Yeah, I think I'm going to go ahead and stick with A, just because at this point in the lesson, what we had been taught was doing it by hand.
Okay.
Okay. Well, let's move on to 6 so we can go through things.
And then we'll come back around
So-
Minette, and we'll come back and do those first ones again after.
Yeah. Do you want to start on 6?
Yeah,
And then
after we get finished, so
circle.
you can take off if you need to. So
Okay.
6, this was the one I was having trouble with. So to assess the accuracy of a laboratory scale, a standard weight that is known to weigh 1 gram is repeatedly weighed a total of n times, and the mean of the weighing is computed. Suppose the scale readings are normally distributed with unknown mean, u, and the standard deviation 0.01 grams. How large should n be so that 95% confidence interval for u has a margin of error of different than 0.0001? So I finally got A. 1960.
Okay, that's different than what I got.
Oh my gosh, are you kidding me?
That's different from what I got.
Oh man. So what did you get? Oh boy, I got C.
What'd you get, Minette?
Okay,
I got C.
I got A. Okay, shoot. What did?
Oh
and
man.
Oh,
what did
whatever.
you get, Karina?
I got A.
Okay, so the formula is Z times the standard deviation divided by the margin of error, and then it's squared.
Mm-hmm. Yes.
So I put the one.
Maybe we're doing the same thing on this one.
Okay.
Okay, let's see.
Let me look
So
at 5.
1.95 times the standard deviation, which is 0.01 equals 0.0196, and then
Mhm.
that is divided by 0.0001 gives me 196, and then when I square it, I get
Oh, I didn't square it.
38,416.
I did square it. I left the square off.
I didn't either.
So
I think that's the problem there.
you're using for the z-score 1.95 instead of 1.96?
Oh, I'm sorry. I was thinking 95, but no, it's 1.96.
Okay, that's what I thought. Okay, so you said
I didn't square. I left off that portion. So I think that's my problem.
I think I did the same thing.
You know, I kept doing that's what I had kept doing. I had kept doing it without the square until I found that part in the book where it gives you the formula that I sent to you, Kimmery.
Yeah. And still with that formula, I left off the square. I'm getting worried by every problem now for the test.
Because it's great when it's always the same.
Can I ask, what is this? It's 1.96 times 0.01 divided by the square root of the.
No, it's 1.96 times 0.01, which is the standard deviation, and then it's divided by the margin of error, which is 0.0001. And then you'll take that number, which when I worked it out, it was 196, and then when you square it, you get 38,416.
Perfect. Sorry, I just part of my the margin of error.
I just didn't square it. So if you guys look at Chapter 10, Section 5, Sample Size Calculations, it says, so there must be an easier way than going through all these steps to figure this, and it says, this gives us the sample size formula which tells the number of observations required in order to obtain a specified margin of error. And it's n equals z times the standard deviation divided by the margin of error squared.
Let's see. I see what you're saying. The trick is to solve the margin, but you're not solving for the margin of error. They give you the margin of error. So if you're solving for m, that would be the correct formula. But you're not solving for m because they've given you m.
Yeah, so this one is just to obtain a specified margin of error.
Yes. And so what the question's asking us is to find a specified sample size.
So is this the wrong formula?
Well, look, if you look at the sample size calculations, and it says this gives us the sample size formula, which tells you the number of observations required in order to obtain a specified margin of error, and then you go to the down below, n equals z times the standard deviation over m, squared.
Yeah.
So it's just flipping it.
So I guess it's a matter of figuring out what you're solving for. So if we're solving for a sample size, we use that bottom formula. If we're trying to solve for the margin of error, then we would use the top formula.
Mm-hmm.
Yeah. So yeah, I think my problem, I just didn't square it. So squaring it, I get 38,416.
Sweet.
And that really is what the formula tells me. So.
Can I do number 7?
Sure.
Sure.
I got A. What did you guys get?
I got A.
I got A.
Sweet.
Yay.
By the way, where am I?
Okay.
8 kind of threw me off, though. A little bit. I chose B. What did you guys get?
I got B.
I got B also.
Wait. Oh, Karina, what did you get?
Okay, 9 kind of threw me because none of them really made sense to me.
Hold on. What did you get, Karina, on 8?
Oh, I see what I'm doing. Okay. Okay. 7 I got A, yes. 8 I got, where am I?
Wait, 7? What? Oh, 8.
She's just going back over her.
Yeah, I got mixed up and my brain was looking at 8 instead of 7 when you guys were on 7.
You're like, man, these girls are messed up today.
So for 8 I got B.
Okay, awesome. Okay, so 9.
Me too.
9 I got A.
I got A as well.
Okay, explain this to me because I could not figure it out. This is what confused me about this one. Can you use an ANOVA hypothesis test to answer this question? Well, ANOVAs are never bell-shaped, are they? They're always right-skewed. So how could it be yes?
Hold on a second.
What?
You could still be bell-shaped and right-skewed, can't you?
That's true. Right?
So in the notes for the requirement, it never says that it has to be, that it can't be bell-shaped. I mean, when you look at the requirements, it says that all of the samples need to come from random sampling. The samples are independent. The populations have some same variances, or that the largest variance is no more than 4 times the smallest variance, and the variance is the standard deviation squared. So then the data are normally distributed for each group. So when you look at the information given, and we have a random sample that's taken,
Yeah.
There's a bell shape with no outliers, which and then the standard deviations are nearly equal, which would be very similar to the variations being the same.
Yeah, I got A. What you got?
What did you put down for 9, Kimmery?
Well, I just put C because I couldn't find the right answer. So that must be the thing, is I swear in one of the videos, he said, ANOVA, you will never have a bell shape. But maybe I'm just imagining things up in my head.
Hold on.
But I know, I know it has to be right. It's always right skewed.
Karina, what
They're
Yes,
never
it does.
negative.
Yeah, it does. It says it is right skewed.
Yeah, which it does say that.
Because the question states that it's bell-shaped, I think that they're saying that it is.
You know, when I look at the example that I wrote in my notes, even of the right skewed that he had drawn, it still looked somewhat bell-shaped.
Okay.
So
maybe that's it. I just thought he had mentioned that it was never bell-shaped.
But it says that there's no outliers, which would mean that it
Yeah.
would be right skewed, right?
But it has to be right skewed.
That's okay. Now I'm rethinking
For
9.
ANOVA, right? I mean, I was totally, I don't know on this one. If you guys all got A, then maybe it's A. I could not figure that because it really just didn't make sense to me.
I'm gonna guess A.
But my little brain sometimes doesn't work as well as other people, so. I mean, I'm totally fine putting A because this one really confused me. Understanding the right skewed and so forth. But if there's,
I'm seeing it is right skewed. I'm not seeing that it's like that there's a definite has to be, but I mean it does say on my notes that it is right skewed.
Right. Because I mean that's the first characteristic of an F distribution is it is right skewed.
Yeah.
But like you said, some bell shape can be right or left skewed, right?
Yeah.
So let's just stick with A.
Okay.
Because I didn't think C was necessarily the right answer. I just didn't know what else to put without, I thought it could not be A. So.
Yeah, in my mind it would have to be A or C.
So for the F distribution, it has to be right skewed.
So I think I was just understanding it wrong.
No, I think you brought up some really good points. I mean, now I'm looking at that bell shape, and that didn't concern me before, but now I see that says with no outliers, which the outliers are what cause the right skew. I think.
I don't want to make you guys second guess just because I couldn't figure it out.
Maybe we should come back to it.
Yeah, let's come back to it because that honestly, but we've done that in the past where we've had ones where we've had to come back and look at, and because we came back and looked at them, we got them right.
Right.
So maybe let's kind of mull it over for a moment and come back to 9.
So for 10, I got D. I first picked B, but I went back and read about the errors.
I put A.
I put B.
I put A.
What?
Oh shoot!
Oh my gosh.
Oh goodness. Okay, so let's read the question.
Hold on.
I put A also.
Okay. Let me just bring my notes back up to that page. I actually just went through and watched that whole video again today because this part always throws me. But let's take a look at it. So a medical researcher is working on a new treatment for a certain type of cancer. The average survival time after diagnosis for the standard treatment is 2 years. So the null hypothesis is that the average survival time after diagnosis is the same for the new treatment and the standard treatment. In an early trial, she tries the new treatment on 3 subjects who have an average survival time after diagnosis of 4.5 years. Even though the sample is small, the null hypothesis would be rejected at the 0.05 significance level. So they rejected the null. Consequently, she rejects the null. In a future study, it is determined that the new treatment does not increase the mean survival time in the population of all patients with this particular type of cancer. The researcher has, and I have that in my chart thing, it says that if, let's see, if you reject the null, so you reject the null, and it turns out to be that it is true, that it turns out that the null was true, that you've committed a type 1 error. If you do not reject the null, and
That's right.
and the
You're right.
the
It's
alternate hypothesis turns out to be true, then you've committed a type 2 error.
Yeah, I'd say.
See, and that's what I have in my notes. Whenever we
Okay.
reject the
My
null, we
brain
say
just
that
thought of
type
it
1
backwards.
error is committed.
Yeah.
Okay.
So then for 12, did everyone get D though?
Yes. Wait, 12?
I'm sorry, I mean 11.
Yes.
Oh. 11, D, yes, D. On 11, yes.
Wow.
We're really batting 1,000 today. Okay.
12. For real this time.
I also got D.
I did too. Okay, good.
Okay, wait. On 12, you got D?
Yes.
Reject the null
Okay.
because the significance is low. I mean the
I got B. So you guys have to work this out, right? Just make sure I use the right formula.
Okay. You do X.
Use the formula Z equals X minus U divided by this.
X minus U, mu, divided by the standard
Is
deviation.
that the formula you guys?
Yeah, divided by the sample size.
Yeah.
And that gave me a 0.08 or 388.
Okay, that's not what I got. Okay, let me see.
I'm going to work through mine again too.
So the so we start with the square root of 100, which equals 10, divided by 0.17. Equals 0.017.
Mm-hmm.
And then we have 1.53 minus 1.5, which equals 0.03. Then divide by 0.017.
Yes.
Which equals 1.7647.
Okay, and then you plug it into the applet.
That's what I didn't do.
Okay. Because then you would plug it into the applet, and then you would highlight to the right, because you're only looking for a content that is higher.
Oh my gosh, I swear I'm stressed for this test.
It's going back and remembering all that stuff that we've done before, and it gets a little bit stressful, but we can do it.
You know, the funny thing is I felt so much more comfortable with this section, so I thought I was doing better on this section, and I didn't feel as
stressed,
as worried as the other one.
It's just keeping all of them straight is
right.
what it is. Like the difference between all the
Yeah.
different kinds of tests. That's really what the issue is.
You know what I did?
Yeah, I agree.
In my notes, I wrote down, and it seemed so crazy at the time, but I'm glad that I did. I wrote down like every single step. Even if I'm like, oh, I already know how to do this, I wrote down every single step. So when I go back and look at the examples, I have every single step written out for me, which I need.
Yeah. Well, obviously I do too. Okay. Okay, so D.
And then for 13, I got D2.
So good, me too.
13. Yep, I did too.
As well as for 14. I got
And 14.
Me too.
But then 15, I got B.
Are you getting these, Minette?
Yeah, I'm writing down because there are some. We can go back after
Okay.
we go through. There are some that I have questions on.
Okay.
Did you guys get B for 15?
Yep.
Yes.
What did you
16, I
get?
got D.
B.
B for
15.
15. Okay.
And then for 16, D.
Yes.
Yep, me
And then
too.
8 for 17, D.
Yep.
Sorry, I'm just
17
running through
what?
mine.
17D.
I'm sorry, D. Okay, me too.
And then 18, I got C.
Also got C.
Not me.
Oh, okay.
Oh my gosh, I'm so stressy
So-
now.
It's okay. It's
What
okay.
did you put them in backwards, Kimmery?
I may have, but I thought it always gave us the same answer. Because I got A, -770 and 5764.
Yeah, putting them in backwards wouldn't change that.
Okay.
Putting them backwards you would end up getting a
Yeah, it would be like
negative.
the same numbers. They would just be
Yeah.
inverted.
Yeah.
Yeah.
Okay.
Independent sample.
And did you put it to 95% confidence interval?
I did.
That is so strange. And did you
Let me
copy
just
and
plug
paste
it in
them
real
all?
quick and just see. Well, we can come back. I mean,
I would say,
Okay.
how are we on time for you, Karina?
I have to hurry.
she's gonna go, so let's
Okay,
just
let's
go
just
through
let's
the
run through
rest.
these, and then if you want to go on the test and put it in on your own, does that
Okay.
work for you? And
Yeah.
then we'll go through the rest of let's go through the rest of them, and then we'll go back and we can answer Minette's questions, and then
Okay.
Kimmery and I can run through those numbers again.
Thank you.
You're welcome.
Awesome.
Okay, so 19.
19D.
I got E.
I got
I did E also.
Oh, I'm sorry. It's the last one, ANOVA. I just said D, but I meant E.
Because it was the last one.
Yeah.
Yeah.
I was like, what?
Really go. Okay.
For 20.
20, we got C.
Me too.
23B.
B.
21 B.
21 is B.
Okay. Me too.
Yeah. And 22B.
Yes.
23C.
Yes.
24A.
Yes.
25B.
Yes.
26B.
Yes.
Okay.
So I think actually, Karina, the only one that you and I ended up getting different on was C, but then we figured out the squared, doing the squared changes the number, and then and 5. I think it's just kind of a difference either with Excel or doing it by hand, and you can make a personal choice there. But everything else we got
So
the
you
same.
guys froze up. What did you have in 26?
26, we got B.
And 25?
25B as well.
Yeah.
Okay, good.
So, is it okay if I go then?
Yeah.
Thank you.
Thank you so much.
Okay.
Yeah, I'll just send that
Thank
in,
you.
and then next week we can talk about how it went.
Okay, that sounds good.
I'm so worried. Okay, sounds good.
Okay.
Okay.
Have a great weekend.
Okay, bye.
so for number 1, I put
Okay,
A.
let's go back over. Hold on, let me see. Number 1, what did you put? A, yes.
Number 2, hold on, sorry. Oh. I guess I didn't mark number 2. Part of it cut off, so let's see. Hold on. I would say it is satisfied because it is random. So yes, and I would say because of the central limit theorem, A?
I put B.
Okay.
I put B
I put B.
also.
And the reason I put B, and probably Kimmery as well, is because it doesn't talk about the sample size, but it tells us that they had to create QQ plots for both the random samples, and that they saw that they were approximately normal. So if it gave us a sample size that was larger than 30, then I would have picked A.
Yeah, I agree.
Okay. So for 3, I put
D, is that what you said?
yes.
Yep.
And
Yeah.
4, I put B.
Yep.
Yeah.
And 5, we already talked about 5. We're going to kind of, I picked A, but
That's what
And
I
I
think.
think that's right.
I think that's right.
Yeah, I do too. I think I just multiplied first, and I should have used the exponents first.
can we run through some formulas really fast? Is that okay?
Sure. Let's start with the formula really quick. That is. Oh wait, no. Let's do the formulas and then we can go back and run through 18.
If you guys need to go, I totally understand. I don't want you to have to wait.
No, you're
No,
fine.
I'm good.
Which formulas are you looking for?
And I'm good.
Okay, so
It helps solidify it in our mind.
I know.
Yeah.
Okay, so let's see. Okay, so can we run through number 5 really fast and how we got that? It was the z times the sigma over the square root of it. Okay. And then we, what do you call it? Squared it.
For number 6.
So
Oh, sorry. I'm looking at 2 different things. So that one we don't square. But the second, number 6, we square. And we got C.
yeah.
Mm-hmm. So the formula, Minette, for 6 you can find in Chapter 10, Section 5. Ruth sent me this. And so
Perfect.
it's n equals z times the standard deviation over the margin of error squared.
Yeah, so 1.96 times 0.01 divided by the square root of 0.0001, right?
Mm-hmm.
Yep.
And then squared, because I forgot to square it, so.
Oh, yeah, 196 squared equals the 38,416. On number 5,
Right.
that one really fast.
Yes, this was the one you missed. We talked about this one in great detail.
For a long time.
Okay, so the formula is x bar minus z times the deviation divided by the square root of n.
Yeah, okay. So we have
What we had decided in going through this is you would work out the fraction, what is in the fraction first. And so you would do, first you would work out the square, or the square root, so that you would do the square root of n, which gives you 2.
Oh, wait, hold on. Would it be 62?
Well, it says there's 4 samples, so the square root of 4 is 2.
Oh my gosh, I thought you said 64. I'm sorry. And that was totally throwing me off. So yeah, square root of 4 is 2.
Yep, and then that's divided by 2, and that gives you 1.
Yeah.
And then you would times 1 by 1.96, which gives you 1.96. And then you would plus or minus that by 1,000. So if you plus it, you're going to get 1,100 or 1,001.960, and if you subtract it, you'll get 99.8.040.
Yeah, okay. That makes sense.
And part of the reason why we discussed this at length is because Karina had plugged it right into the to Excel.
Okay.
And when you plug it right into Excel, the numbers that you come up with are actually B.
Oh, I see.
So so we were trying to figure it out. So we were trying to plug in different numbers and see what the difference is. And the Excel always has just a little bit of a difference.
Right.
In some of those numbers, like some of the beginning ones that we did. So I think Kimmery and I just kind of elected to go ahead and use A because it was coming out correctly with when you do it by hand. And when we plugged in numbers from 10's preparation assignment and tried to see if the Excel came up with the same numbers, there was a little bit of a difference in the numbers from the answer key.
Oh, wow. Okay.
Well, and the other thing, if you look at the formulas, it's higher than the x minus or x plus the multiplication. So that makes me think we do the division first and then do the other with the answer.
Okay. That sounds good. So, numbers.
I just realized that what she may have done, and maybe this is what you may have done, Kimmery, is that the 95, when you get a 95 confidence interval, normally that's 2 deviations away from the mean. When you use the 68, 95, 99 rule, you would take 2 standard deviations away from the mean.
Which one are you talking about?
Talking about 5.
Okay.
So if you actually take the 1.96 and times it by 2, you're going to get and then use that number to run through the problem. That's when you would get the 1003.920 and 996.080. That's where the difference would be. But in the examples that I'm seeing for the 95% confidence interval, you don't need to take that z-score for the 95% confidence interval and times it by 2.
And I Googled like the order that you do multiplication.
Yeah.
Or I mean equations, and it says, and I hear my girls say this all the time, please excuse my dear Aunt Sally, which is please, parentheses first, excuse is exponents, power, square, roots, etc. next. And so we would do that next, and then we would do the multiplication or division.
And then addition.
Well, I think that's pretty. I was trying. The only thing that was sticking in my mind was how would you then get the numbers in B? And the only thing I can come up with is that if you were to take that 1.96 and times it by 2, and then you get 3.92.
Right.
And that would give you those second set of numbers. But there's no reason to times that by 2.
Before you do the division.
Yeah, that would be before you even did the problem.
Well, if you multiplied 1.96
times 2. I see what you said. That's where you get the 3.92. That's right. Okay.
Right. And then you divide it by 2. So
divided by 2. And that still
that's
just
where
brings
that
you back
difference
and it still brings you back to 1.96. Okay, I'm getting that now. I see how it could have. Okay. Okay, but still A? We're still good with A?
I'm going with A.
I'm good with A.
Okay.
It makes sense to me.
Okay.
After looking at everything else, it makes sense to me.
Okay.
A lot of things weren't making sense to me, so this helps.
Number 7, I got A.
Number 10?
7.
Oh, 7? Yes.
7, yes.
8, I got B.
Yes.
Yes.
And A.
10 or 9, I got A.
Okay, so 10 is one that I have questions about.
Okay, let's go over that one. Let's come back and just look up 9. I wanted to actually type in maybe in a search engine the requirements for a ANOVA hypothesis and what makes up a ANOVA hypothesis. If we can look over those and see.
Yeah.
Let me.
but the only other answer that would make sense in that question would be C.
Yeah, and that's what I ended up putting because it just wasn't making sense.
Yeah.
But I can see what you guys are saying too. It never specifically says it cannot be shell-shaped, but the outliers threw me, and I knew it had to be right skewed because that's one of the main characteristics of it.
So why don't we let's go through the rest of this and then let's see what we can find out about that with 9. Just making another mental note to come back on 9. Okay, so what was your questions, Minette?
So 10, I put D. You guys got A?
Yes.
A, yeah.
So, okay, so hold on, let's see. Even though the sample size is small, the null hypothesis would be rejected at the 0.05 significance level. Consequently, she rejects the null hypothesis. In a future study, it is determined that the new treatment does not increase the mean survival time in the population of all patients with this particular type of cancer. The researcher has... So, she rejected the null, but she came back later.
Okay, let's look at D and C and D first and show why that wouldn't fit here. So if you look at C, incorrectly use the 0.05 insignificant or insignificance level. Significance level, when you should have used a 0.01 significance level. The significance level has to be stated before any test is run. So it's already stated for us that it's a 0.05 significance level, and so at no other time should it ever be changed, unless you're going to redo the test at a different significant level, and then you would do everything all over again.
Right.
And then here in D, incorrectly used the significance test when she should have computed the p-value.
Okay.
It's kind of tricky because the p-value is what we're going to compare the significance level to. There's not a significance test per se, but there is a test that we run in order to get the p-value.
Correct.
So as long as we have the p-value, which is what we needed to do, we got the p-value. Or wait, no, she didn't give us the p-value.
No, we had the significance level.
Exactly. So the p-value would be compared to the significance level to then tell us whether or not we would reject the null or we would fail to reject the null. So we'll let go of those two down below because one is not possible if you run the test correctly, and the other is basically, it's almost contradicting itself when you have to have both of them. You're not going to ever compute the level of significance, but you are going to compute the p-value, but you're going to compare them against each other. And so it's not possible to incorrectly use the significance level because that's not going to change.
So you guys got A because she rejected the null. And anytime null?
Go ahead,
Yeah,
Kim.
and then in chapter 9, it states, a type 1 error is committed when we reject a null hypothesis that is in reality true. So type 1 error, whenever we reject the null, we say that a type 1 error is committed.
Okay. I guess I was hung up on when it is true. You reject the null. I forgot what I was going to say. Sorry.
It gets confusing because when you commit a type 2 is when you fail to reject the null, but in reality the alternative hypothesis is true.
Okay. So the null. Okay. 10 A. So 11 D.
Just one more thing real quick on that, Minette.
Yeah.
Right under my type 1 error is committed when we reject the null. it says the value of A, which is the significant level, is the probability of getting a type 1 error.
Where is that? Chapter 10?
That's chapter 9. If that helps any.
I'm still really confused. That's okay.
I think for this, whenever if it comes in the test and it talks about rejecting the null and finding out that it, in the end, you find out that it's true, that the null was true, that it's a type 1 error. If you fail to reject the null and you find out that in the end you find out that the alternative hypothesis was true, then that's a type 2 error.
Okay. That makes more sense. Awesome. Perfect.
But you know what Kimmery just said, I mean that's what you're testing against. You're saying that you have a 0.05 confidence, or not confidence level, significance level, that or the probability level that you're going to commit an error.
The type 1 error. Yeah.
Yeah. So that's why if it falls below that, then the level of significance shrinks, and your likelihood of committing a type 1 error shrinks as well. But then the likelihood that you're committing a type 2 error increases.
Okay. So that's where you're saying
Right.
11 is D.
Yes.
Okay. And 12 is D.
Yes.
Can we run through that one really fast?
The D. Okay. So that's the one that Kimmery was just working on. So that's we can run through it real quick. We do it says that X bar equals 1.53, and we're going to subtract that by the mean, which is 1.5, and we're going to divide that by the standard deviation, which is 0.17.
Hey, Kristen.
And then that's going to be divided by the square root of 100.
Okay.
Okay, so we start with the square root of 100, which is 10.
If you need help, ask Avery nicely.
So 10, so then it's 0.17 divided by 10, which gives us 0.017.
So my calculator always rounds up. I don't know how to take that off. I can't use it. Sorry.
That's right.
Let me try my phone. Okay.
Okay, you ready?
Yep.
Okay. Now we can work on those top two numbers. So it's 1.53 minus 1.5, which will give us 0.03. And so we'll divide that by the number we got before, which is 0.017. And that will give us 1.7647. And then we have to open up the applet. And we'll put that applet into the z-score on the right-hand side. And we'll highlight everything from that score to the right, because we're looking for, the problem asks us to see if the mean nicotine content is higher. So we're looking for a greater than number.
Okay.
And so when we get that, the p-value that we get up at the top is 0.0388.
Okay.
Which ends up being less than our 5% level of significance. So if the number is low,
Project the null. Awesome.
yay! Okay. So 13, what did you get?
13. D.
Okay.
I think the rest we went through the rest with cleaner.
Okay. And we did pretty good. And then we went to 17, no, 18. So this is the one that you were looking at, right, Kimmery?
What number was it?
18. With the used Hummers.
Yes. Yes.
Let's go back and work
Okay,
through
so
that one.
I'm gonna, yeah, let me get this up.
Okay.
So, which of the following is a 95% confidence interval for the true difference of mean listing prices? Okay.
Let's see.
So used Hummer.
Okay.
Oh shoot.
Okay, so the used Hummer, where is that at? There we go. Okay, here's my used Hummer information. Wait, where's my used Hummer information? Nope, that didn't work.
I know, I'm trying to go. I pulled it up on Excel instead of SPSS, so I'm going to go back.
Okay. Oh my. Okay. So mine just came up. And so we're going to separate these between the two cities. So that's going to be, we're going to go up and transform. Are you there? I'm sorry. Are you there yet, Kimmery?
Oh, sorry. No.
Yeah,
I'm almost there. Hold on. My computer is way slower than yours.
mine went onto SPSS. I'm trying to figure out how to get it onto Excel because I can't get into SPSS.
You know, the Excel one,
there should be. Difference in listing between numbers for Los Angeles, for New York. Okay, so then I transform.
Yep.
And I do the automatic recode because we're doing the independent samples.
Yes, we're doing a difference. We're doing the difference. So you would take the cities because it's between Los Angeles and New York.
And so the city goes in the variable?
Yeah. Hold on a second. Sorry, we went to the wrong place. So if you just X out of that and go back to transform, we're not gonna recode. We're gonna go to compute the variable. Oh wait.
No,
that was the other one. You're right. Sorry. Nope, we are recoding. I'm looking at two separate notes for both of the things that
Okay,
we ran through.
cool.
So you'll go to the
Just
city
to clarify then.
and you'll recode the cities.
Okay, so the computing we do with dependent samples, right? And recoding we do for the independent.
Yes, because otherwise you'll have
Okay.
the string variables that can't be computed.
Right. Okay, so we are not computing, we are recoding.
So you're going to recode for New York and Los Angeles.
Okay.
And then you can do the statistics test for the price as the dependent variable and the recode for your factor. Okay, and then we can go back and we can do the analyze and compare the means for both
So when you define groups, did you just put 1 for 1 and 2?
Yes.
Okay, so we're look at something different. I don't know.
I'm going to go grab my laptop and see if that will let me in.
Okay. So yeah, so when that comes up
analyze
for
and
me,
explore.
and then the number that you should be using, remember that you use the bottom numbers for the independent.
Okay, wait 1 second. So are you after you've done the independent sample test, t-test, are you going back and doing analyze descriptive statistics and explore again?
I did not, but I can try that again.
Oh, okay. No, that's okay. I think that's what I did. So let me just look and see what I came up with before I did that. Okay, see, when I do this, it says, warning, the group subcommand, so it will not even calculate anything for me.
Okay, so let's erase everything and let's go just step by.
Okay. So if, let me see.
So I'm gonna click out of mine, and then we can walk through it again.
Okay.
And then
Sorry.
hopefully then we can figure out what the problem may be.
Okay. So I pull up the information for used Hummers in LA and New York.
Mm-hmm.
And then I go to transform.
Okay, so here, if you follow the steps that were in the video, you can do the histograms. It doesn't ask for a histogram, so I mean, and then you can click on it later on. So here, let's take it to what it tells us to do step by step. So it tells us to go to Explore, so descriptive statistics, and go to Explore. And it wants us
before we transform?
That's kind of, yeah, that's kind of weird that it says.
Okay.
And it just has us put the group variation in the factor list.
So what's it splitting it by? Because I don't have any groups listed yet. Okay. So anyway,
mine does split it by the by Los Angeles and New York. It doesn't give me anything else. But I think it's just to kind of run it. Then it tells me to go back in and do the recoding. So you don't necessarily have to go back in and do that first one with the descriptive statistics or the histogram, but you do have to go back in and recode.
Okay, so when you did the first step, analyze, descriptive
Yeah.
statistics, and explore, what did you put in the dependent list?
It says, on my notes, it says do the analyze descriptive statistics, go to explore, and then in parentheses I have put the group variable in the factor list box.
So there's a dependent list and a factor list.
Yeah, the factor list would be the city.
And the dependent list is the price.
Yes. So when I just did that by itself, it let me run that that statistic, or it let me run the explore as long as I didn't put the price in.
Wait, you did not put the price in the dependent list?
Let me double check on that.
I'm getting more confused.
Sorry. No, I'm sorry. I did. I put the price in. I put the price in, and then I put the city in, and then I was able to run that statistic test. All it does is run the mean, and it runs some of the numbers that are in here, so you can get like the standard deviation for each of them.
Yeah.
So it just gives you some data information, but then you go to transform, and then we can code, because we're going to separate those out. So essentially it took those things, kind of put them together as one. So now we're going to separate them out.
So recode, I do
city.
City, okay.
Okay, and now we can go back to analyze, to the compare means, and we're going to go to the sample independent samples t-test. So then we'll go ahead and put the price back in the test variable, and the group variable will put the recode and define the groups. It sounds like you got to this point before, right?
Yeah. So compare means independent sample t-test.
Yes.
And then price in the test variable and city
do recode
in the group variable.
You're going to do your recode in the group variable.
Okay, I think that's what I did. Let me see. No, I didn't do the recode. Oh, I hadn't recoded just that time. I don't know. Maybe I didn't. Maybe that's my problem. Maybe I didn't do the recode there.
Okay. So try putting in the recode, and it should ask you how you want to define them. So then you would put 1 and 2 in as your definition.
And I'm pretty sure I did that, but I can't remember, to be honest.
Okay.
Okay.
So let's go ahead and press OK.
Okay.
Okay, and then did that come up?
Yeah, so then independent sample test.
So you go to your independent sample test, and we're looking at the
lower. Okay. Yeah, I've got independent sample test.
See how it has the two
and I have
sides? It has the equal variances assumed and the equal variances not assumed.
Right.
You're always going to use that bottom level. So you're always going to use the equal variances not assumed.
Okay, see, that's my problem. I thought we always use the top.
Nope, we always use the bottom.
But like all the test statistics are on the top. So just for the confidence interval, we always use the bottom?
No, it's always all of these down below on the equal variances not assumed. Those are the scores down below for the independent samples test. If you look at the scores up above, the equal variances assumed, that starts to get us into that same level of like the ANOVA tests, where the variances have to be equal.
Okay, let me just make myself a note so I can't. But if you look at it, that's what I was doing different. I was looking at the top.
Yeah.
So I did it correct, I just read it wrong.
Let me just see here. Yep, and I see what that did too. Yeah, because then you would round that up to 770, and then that does give you that same score.
Yeah.
That you came up with.
For some reason, I thought we always used the top.
I think just with this one here, with the differences, that's where you get the DF right here.
Yeah.
Lost on what the DF stands for right now. The degrees of freedom. That's when you get degrees of freedom that break off into decimals. Because before it was really easy to identify the degrees of freedom, because the degrees of freedom is just 1 minus the sample mean.
Okay.
But when you have,
that makes perfect sense.
Yeah.
And now I see what I was doing. So.
Yeah. Awesome.
Cool. So let me see. Was there anything else besides just that ANOVA one?
So which one did you have on the ANOVA?
Oh, the only other one I had, 22. You guys put B?
Yes.
Because I had put A. So let's see. To conclude that the bone density of at least one of the groups is different from the bone density of at least one of the other.
This you have to, when you go to the ANOVA, remember that when we do the ANOVA, that the null hypothesis is always that all of the means are equal. And the null hypothesis is that one or more of the means differ from the others.
You mean the alternative?
Oh, the alternative. Thank you. The alternative is that one or more of the means differ from the others. And so if we're rejecting the null and we're accepting the alternative hypothesis, then we would say then we would just put in the wording for the alternative hypothesis after we say there is sufficient evidence to conclude that the bone density, and then the rest is the alternative hypothesis, which is one or more of the means differ from the others.
Okay, yeah, for some reason
if it wasn't, sorry, go ahead.
No, I was just saying for some reason I mixed
an ANOVA test. Yeah. If it wasn't an ANOVA test, the sufficient evidence to conclude that the bone density of all three groups is about the same, that would be correct. But because it's an ANOVA test, and that's what the null or the alternative hypothesis is, I think that's why I chose B.
Okay, I'll just read over that a little more.
So now should we just input it?
Well, we wanted to run over number 9, right?
Oh, that's right.
Yeah, number 9.
So,
and I'm sure you guys are right.
You know what? Better safe than sorry. So.
Yeah.
I took it in, but it didn't make any more sense.
Let's see. One-way ANOVA test statistic. Differences between two or more independent variables. Assumptions. Assumptions. So you assume that the dependent variable.
Okay, so
I typed in something else so that I could maybe it would say it a little bit better, but it's not really. Oh wait.
Well, let's see.
Here's number 4. The assumption that I brought up. There's 6 assumptions, but one of the assumptions says that there are no significant outliers.
Okay. Let's see. I think you're right. I just remember hearing it say something about not being shaped, but it probably didn't say that. It just said it must be right skewed. It is right skewed.
So here it says skewed distributions could be considered approximately normally distributed if the skewedness is negligible and their shape is otherwise approximately normal.
That's for an ANOVA.
Yeah. Bell-shaped is not a term that means anything much in hard practice. I'm just looking, somebody else typed in that same question. I just Googled it.
Mm-hmm.
But bell-shaped still considered as normal distribution for ANOVA, and that's the answer they got.
I think it sounds good.
Yeah, I mean, I think you're probably right. Assume each group is normally distributed. Just that bell shape kind of confused me. So, but that's what I mean. Like that was one I had a big question mark by because I just wasn't sure.
Right.
So yeah, if you guys are comfortable with it, I think I feel good about. I feel more stressed about the test now, but I feel good about inputting this.
Okay, why don't we go ahead and put it in?
Yeah, that sounds good.
I think
So
we're about as good on this information as we're going to get. If there's something wrong, I think we've done well on trying.
I agree.
Okay.
Okay.
So shrink this down. Okay, so let me just open up the quiz. Okay. Are we ready, ladies?
Ready or not?
I think so. Here we go.
Okay. So I attended my group meeting. Yes!
Yay,
we got that one
right.
Okay. So number 2, we are saying is A.
Mm-hmm.
Number 3, we are saying is B. Just make sure that they're not switching anything up on us. Okay. Number 4, which would be number 3 in our thing, would be D.
Mm-hmm.
Okay. Number 5. Now here's a difference. So
Yeah.
We have
don't
a
see.
question 5 here that is not one that we went over.
5 is, all right, oh wait, a researcher.
This is a new question.
No, that's number 4.
That is number 4? Oh, I was looking at the wrong thing then. That's why.
See, I did too at first. So that
Okay.
is number 4.
Okay, so that's number 4.
So sorry.
Well, yeah, oh, I keep looking at the wrong one. That keeps
I know.
confusing me.
I know, that's what
So-
I'm doing too.
Number
Number
5
5
is,
on the test is B.
is what?
Is B.
B, okay, yeah. I thought you said C.
No. You're like, no, Ruth, don't do this to me. Okay.
Oh, okay.
Number C is A.
Number,
Or number 6 is A. I'm really getting tired. Okay. Number 7 is C.
Number 8 is A.
Is A. Okay. Number 9 is B.
B is in boy?
B is in boy.
Okay.
Number 10 is A. Okay. Number D is, or sorry, number 11 is A.
It's been a long night.
Yes, it has. Number 12, sorry, go ahead.
No, I was just saying it with you. A, B, C, D.
D, very good. Okay. Number 13 is D. Just let me know if I'm calling out the wrong numbers again. I'm nervous about that myself. Okay, so number 14 would be D.
Okay.
Number 15 is D.
Number 16.
Go ahead.
B.
Yes. 16 is B.
17, D.
17 is D. Okay. 18 is D. 19 is C. 20 is E or ANOVA. See, 21 is C or 7.978. 22 is 0.002 or B. See, 23 is B. 24 is C. 25 is 1.685. 26 is 0.096 or B. That last one was A, sorry. I just gave the number. And 27 is B. Okay. So why don't we go back over them again if somebody wants to read through them this time just to make sure we're all on the same page.
Okay. 1 is true.
Mm-hmm.
2A, 3B,
Yes.
4D, 5B, 6A, 7C, 8A, 9B, 10A, 11A, 12D, 13D, 14D, 15D, 16B,
Mm-hmm.
17D, 18D, 19C, 20E, 21C, 22B,
So
20. What was that?
you froze up at 12. I didn't hear anything.
Okay,
Oh,
let's go back to
12 and
12.
beyond.
I'm so
Let's go
sorry.
back to 12. Okay, can you hear me?
I can hear you.
Yeah.
Okay, so 12 we have D. 13 we have D. 14 we have D. 15 we also have D. Wow, we have a lot of D's in there. 16 we have B. 17 we have D. 18 we have D. 19 we have C. 20 we have E as in Ethan. 21 we have C. 22 we have B. 23 we have B. 24 we have C. 25 we have A. 26 we have B. And 27 we have B.
Good.
You ready?
Okay, ladies, let's try it. Yes!
No, wait, seriously?
We got it!
Wow.
Awesome.
That was good. That was good. And it's
Yay,
good because
good.
it answers some other questions that we may have had, especially on 9.
Yeah, exactly. No, that helped a lot. So now I just have to study even harder. I felt like last time after we did the quiz, I was ready to jump in and do the test. I don't feel that now. So
Yeah, right. It's like,
cool.
okay, well,
Thank you so much.
wonderful doing this with
Awesome.
ladies. Good luck on your test.
Oh, good luck to you.
Yes, you too. Thank you.
Okay, I'll talk to you later. Thank
Have a
you.
good weekend.
You too.
All right.
Okay, bye.
Bye.
Bye. Bye, Nanette.